So we are just a little more than 3 weeks away from the first exam. Okay. Just want to remind you that 3 weeks they are not that long. Okay. So before you know it, the first exam will be here. So again, I want to remind you that do not start to study too late. Okay. So these things cannot be learned in 1 week or in 1 day. Okay? So just remind you. Okay? Now I've skipped quite a few mathematical steps in my lectures. Okay? So sometimes you may feel that you're confused by these skip steps. If you do feel that way, please come to my office hour or try to see me by appointment. I don't want you to be confused just because I missed or skipped those mathematical steps, okay? Because I was assuming those math, you should be able to do it, okay? So of course my assumption could be wrong because everybody has different backgrounds, okay? So if you need help, get help, okay? Because if you don't, I would still assume that's okay, okay? Also, you've seen a lot of math in this course. Of course, I don't think that should be a surprise in any engineering course, okay? I'm talking about this because I've got complaints before in previous years of teaching this course. They complain there's too much math, okay? When I saw those complaints, really I was thinking basically, well, we're engineers, okay? We're supposed to use math to solve problems, okay? If you look up the definition of engineering, it's the application of math, physics, and chemistry in the solution of problems, okay? So, I mean, BME is not different from other engineering disciplines. It's different, I guess, only it's a little newer than others, okay? And also, you know, so BME requires how many math courses? Cap 2, 3, EPQ, Advanced Engineering Math, Crop Stats. You count all these courses, like it's like 6 or more semesters math courses, right? So learn this math, well, you gotta use it, right? So anyway, so last time we discussed the Castaño equation. Now we've discussed quite a few of these relationships between shear stress and shear rates. Okay, Newton's law, being plastic, Castaño equation, Power law. Okay, all these in mechanical engineering they are called constitutive equations. Okay, meaning these are equations that are fundamental to these different materials or different fluids, okay? Whether water, you know, blood, Power law, or being plastic. Meaning that once you know a material, you know, that is, for example, being plastic, that relationship will never change, okay? Only the constants will, okay? So that means this equation can be used for blood flow anyway, okay? So this equation, the relationship between the stress and shear rate will never change, no matter where, as long as what? The stress is larger than the yield stress. And when the stress is less than the yield stress, of course, there's no shear rate, okay? Gamma is 0, okay? And then we talked about the Fourier's effect, okay? So of course, if you have worked on the homework problem, I hope you did, And you know that the hematocrit here is less than here or there, okay? So we talked about this observation, sort of. So in the homework, you're going to show mathematically this is indeed true, okay? So, of course, I wonder whether you thought about why. Why does this phenomenon exist, okay? So here the hematocrit is smaller, but here, so basically large, small, and large. How could this happen? Well, basically, here, the flow of the cells is much faster. Okay? So, of course, when you think about hematocrit, you think about it in a stationary or in a stationary way, meaning that you look at everything in still sort of images. Okay? But actually, you know, it's not still, okay? It's flowing, okay? So the reason you have more here, less here, is because these cells are moving much faster, okay? So as a result, so you have this Fourier effect, okay? Now this is also called the flow average, okay? The equations that you see in the homework, okay? You see the HT and HD. These are called flow average. So remember the average velocity, right? So I told you that equation, the integration over a certain surface area A, VZdA, right? So that's an equation you can use for any kind of average on a surface, right? So VZ could be pressure, could be mass, could be anything. Okay, all right. So that's just the average. Okay, so the integration A something dA. That's the common average. Okay, the equation for the hematocrit that you see in the homework, that's called flow average, meaning that there's a velocity, everything's moving. Okay, there's a similar concept in energy transport. Unfortunately, we cannot talk about this. Okay, so that's similar to this. Okay, so basically there is the energy carried by mass going through tubes. Okay, all right. So there you will see that the average will be higher there because here it's flowing fast. Okay, energy. So that's another thing I want to tell you. And of course, you know the marginal zone theory. That's the theory you're using to show that this is true. So flow of blood. Okay, yield stress. Hopefully you learn how to deal with it. So you can work on homework number 2, problem number 2 in homework. All right, so the equation of continuity. So what we were trying to do is what? Well, since for every transport problem, momentum transport problem, we have to use the shell balance method. Why don't we just look at this in a more general way, so that we can derive some equations we use for solving some problems, so that we don't have to go through the derivation for every problem. So that's the reason behind this. Of course, before we look at the momentum transport or the momentum conservation, we looked at mass conservation, and then we got this equation, the equation of continuity, which represents the mass conservation in any control. Okay, all right. So now, I guess one question that we could ask is, well, why didn't we consider mass conservation in any of the previous examples we've looked at, whether it's homework or in class? Why didn't we look at mass conservation in those examples? Yeah.
Since velocity is constant and mass is conserved, or momentum is conserved, then by definition mass is to be conserved as well.
Yeah, so there's no question that there, in those problems, mass is conserved. Okay? Why we didn't use it? That's because, well, even though you use it, you'll get what? you get no new equations, okay? You look at mass conservation, you find out 0 equals to 0, okay? That doesn't help us to solve any problem, right? So that's why we didn't look at this, okay? So you're welcome to look at mass conservation in all the previous problems, okay? You'll find out the only equation you can get, the only equation you can get is what? 0 equals 0, okay? So no use, useless, okay? So that's why we didn't look at mass conservation before. Now, of course, we can write that equation in the vector form. Of course, you don't have to know how to work with this equation. As I mentioned before, this equation can be only applied in the rectangular coordinate system, right? So what about other coordinate systems? And one way is to use control volumes in cylindrical and spherical coordinate systems and go through this derivation, okay? And the other way is to do some vector and tensor analysis and go from here and get the equations in the cylindrical and spherical coordinate systems. Of course, you don't have to do it, okay? It's in this handout number 5, that's on canvas, okay? All right, so the first one you see, of course, is rectangular. That's the equation we derive. If you use the control volume and do mass conservation, you get these two, cylindrical and spherical, okay? So, that's handout number 5. Of course, if you ever need these equations in the exams, they will be given to you, okay? And as I promised, I'll show you the equations that will be given in exams just before the exam, okay? So, and when you start to prepare for the exam, okay? So this is handout number 5. Okay? Now from here, there's one special case we can discuss. That is when this density is a constant. So if you have a fluid with constant density, meaning rho is a constant, what are we going to get? Well, this is 0, right? So then you have this dot that equal to 0. And of course, rho is constant. If this side is 0, you can divide, because this is just a differentiation, right? So rho is a constant, you can put it outside and divide both sides, rho will be gone. So that means if you have a fluid that has a constant density from the equation of continuity, we can get this condition, right? Now this represents that the volume of the fluid, although it's flowing, but the volume is not changing during the flow. So volume, if the volume is not changing, okay, so any volume you're looking at, okay, its volume is not going to change. So its volume, if its volume is not changing, that means what? Incompressible, okay? That means you apply pressure on it, its volume will never change, okay? So that's what this represents. I just want to mention this so you know, you're aware of this, okay? All right? So now we can look at momentum conservation. This is what we have been through quite a few times, okay? So basically we're going to use the shell balance method and look at the momentum conservation, we're going to use the same control volume as we used when we considered the mass conservation. As used in mass conservation. So same control volume, okay? So something like this. X, Y, and Z. So for momentum conservation, of course, we need to look at what? The change in the momentum of this control volume, okay? Equals to E minus L, and generation and consumption, right? So to look at generation and consumption, we need to know what? The forces that are acting on this volume, right? Because forces generate or consume momentum. For the momentum flowing in and out, it's just the velocities, right? So we know how to deal with that. So first, let's look at the forces. So we know there's a body force, gravity, right? Other than that, there are surface forces, okay? Surface forces are the forces acting on the surfaces. So remember, of course, the Newton's law in 3D, right? So on each surface, we will have 3 components of the stress, okay? So, and also you remember the positive directions of these stresses, right? Okay, so let me draw this quickly on these surfaces. So on the top, tau ZZ, tau ZX. This is the same as we've drawn before. And on the right, of course, we have tau Y and Y, tau YX, and tau Y and Z. On the front surface, you will have tau XX, tau XY, and tau XZ. The other 3 surfaces, we have similar symbols, same symbols for different opposite directions, okay? And also at different locations. So remember here, this corner here is the X, Y, and Z. So the control volume, again, it should be at an arbitrary location, okay? So that corner there, that's X, Y, Z, just like before, okay? All right. So, of course, we should have what? Velocity, okay, just like when we consider mass conservation. And so velocity should be a function of time and spatial locations, okay, different components. And we should also have the density and just like before, okay? So, momentum is vector or scalar, remember, right? So vector, hopefully. So momentum is a vector, so that means 3 components, right? So when we consider the momentum conservation, we should consider these components separately, okay? So let's consider the momentum conservation in the x direction first, okay? All right, momentum in the x direction. Right? That's how you calculate momentum, right? Mass times velocity, right? Mass, velocity. Of course, we're considering what? How it's changing, right? So just like mass this is how it's changing over time, right? Change over time. So, and of course, that's the volume. We should put it outside. So rho. Oh, no. So the change, okay, is equal to in and out, okay? So if you remember our discussion about mass conservation, okay, so you know that, well, you look at all these surfaces, right? So first, how momentum can be brought in or out, especially the momentum in the x direction, okay? All right, so look at the front surface, okay? Well, so here, the velocity should have three components, v sub x, v sub y, and v sub z. So on these surfaces, on this surface, which component of the velocity will contribute to the mass coming out? Which component of the velocity will contribute to the mass that's coming out of the surface? V sub x, right? Okay. So, and on the back surface, of course, is the same component of the velocity v sub x that's bringing mass in. Without mass going in and out, and there's no momentum going in and out, right? Okay? All right. So, on this surface, the amount of mass that's coming out, we've already discussed this in mass conservation, right? So, and of course, we're considering the momentum in the x direction, okay? So, how much mass that's been coming out of there? Since it's coming out, it should be negative. So remember, when we talk about mass conservation, this times the cross-sectional area here, that's delta y and z, right? That will give us volume per second, right? Mass per second, right? So rho vx delta y delta z, okay? All right? So that's how much mass that's coming out, all right? So that times what? V sub x will give you the momentum that's coming out, right? So also, if you forgot what we talked about in the mass conservation, you remember this is what? Momentum flux, right? Times area will give you momentum per time, okay? All right? Okay? Okay? And everything here is per volume, of course, so, okay, eventually. Anyway, so flux, right? Times area, that's momentum per second, okay? So that's how much momentum, that's how much x momentum is being carried out from the front surface, right? So by now, since it's coming out, it's negative. And then you look at the back surface. Of course, there the momentum is coming in, so it's plus rho vx at x delta y delta z. So that's how much momentum that's coming in from the back. Okay? All right. So we've considered two surfaces. Now let's look at this surface. So the surface with the y direction or the normal surface. Is there any mass that's going in or out from that surface? Now keep in mind, we're looking at a 3D problem, okay? So far, all we've looked at is a 1D problem, right? All right, So, okay? So first of all, is there mass going in and out on this surface? Yes, right? Because the component V sub y will bring mass either in or out. On this surface, V sub y, that direction, so V sub y is bringing mass out, okay? All right? So we talked about this in mass conservation, right? So V sub y is bringing mass out of here. Since V sub y is bringing mass out of here, do these masses coming out of here carry any x momentum? Yes, right? Because the mass here do potentially have a x component of velocity, all right? It's just that here, that x component does not contribute to the mass coming out, okay? So when you calculate the mass that's coming out, it's rho v sub y times delta x delta z, right? That's how much mass is coming out. That mass times v sub x. V sub x will give you the x momentum that's being carried out of here, okay? So minus rho v sub y, v sub x, delta x, delta z. This is at y plus delta y. So on that surface, see, rho v sub y times delta x delta z. That's how much mass is coming out of there, okay? And times v sub x, of course, this is the x momentum that's being carried out of that surface, okay? So we're only considering the x momentum conservation, okay? All right? So of course, you can consider this surface right here on the side, and then there, mass is flowing in. It's going to carry some momentum in there. So rho v sub y, v sub x, at the location of y times delta x delta z. This is the amount of x momentum that's being carried in on the next surface. Okay. So the remaining two surfaces on the top and the bottom, I don't think we need to discuss those in detail, and you know what they should be. So there is the velocity z, v sub z, that's carrying mass in and out, and that mass times v sub x will give you the momentum that's being carried in and out. So okay? The same process we went through in those simple examples, it's just that here it's a 3D sort of situation. So these are the momentums that's being carried in and out on all 6 surfaces. Of course, now we need to consider generation and consumption. The generation and consumption. So x momentum. So all these y and z components, they don't generate or consume the x momentum. So they are gone, okay? It's these. This one, that one, and that one will generate or consume momentum, right? Okay? So if you look at tau xx, that's in the negative x direction. So this one consumes momentum, okay? How much? Well, tau xx is shear stress, right? So on the front surface, consumes stress times area will give you force, right? Okay. Force is what? Momentum per second, okay? This is how much momentum that's being consumed by that shear stress component, right? And of course, on the back surface, that tau xx is pointing to the positive x direction. So that one generates momentum. And then you look at every one, okay? So this tau yx consumes, okay? So that's negative tau yx at y plus delta y, delta x, delta z. And on the left surface, of course, you have tau yx there at y. And that one points this direction. We didn't draw it, but you should know. So delta x, delta z. And then the top and the bottom. So on the top, it's tau zx, this one, see, consumed, okay? So that's on the top, so it's at z plus delta z, so tau zx, z plus delta z, delta x, delta y. And then tau zx at the bottom, this is at z, so positive x direction, delta x, and delta y. And the last one is what? The body force. We have not calculated that one. So, sorry, not the last one. Mass and g in the x direction, g sub x, okay? So the direction of gravity may not be aligned with the coordinate direction, so it could be any direction. So that's why we need to use the component of that g, okay? All right, so any other forces we should consider? Did we forget something? Pressure. Okay, so pressure is always acting on surfaces and we point to the inside of the volume, right? So that means the pressure here will be in the x or y direction, okay? So on the front surface, it's P at x plus delta x. It's pointing to the same direction as tau xx, right? That's how pressure operates, right? So negative P at x plus delta x, again times the area, delta y, delta z. And then on the back surface, there's the pressure pointing to the x direction, so that one generates P at x, delta y, delta z. Is the pressure on here? Of course, right? So pressure is everywhere. What's the direction of the pressure? In the tau y direction, right? Okay, so that one has nothing to do with the x momentum generation or consumption. The same here, and same here. So those pressures, they only contribute to the momentum conservation in other directions, not in the x direction, okay? So that's all we have, as you can see. A lot of them, okay? So you can see before, for simpler problems, we only need to consider what? Particles, right? So a lot of them are zero for simpler problems, okay? All right? So, for example, for a problem, there's only V specs, then this is zero, right? So, okay? And this is zero. That's why there we had those, okay? So, okay? All right, so this is the 3D. Of course, what we're going to do next is to divide both sides by the volume, okay? And of course, after you do that, how we can get these derivatives. First one here, divide both sides by delta x, delta y, delta z. Y, z cancels. This divided by delta x, you let delta x go to 0, you get this derivative negative, whole thing, right? So, and then here, this difference divided by delta y, and this we get partial this, partial y, right? Negative. Skip that. And then this. So this 2 divided by delta x. Of course, you get partial, negative partial xx, partial x, right? This is partial y, partial z. So this one, you divide by this, you won't have rho g xf for the pressure. So this minus p plus that divided by delta x, you get negative partial p partial x, right? So divide by the volume, and then let delta x, delta y, delta z go to 0. We're going to have this equation. On the left hand side, we'll have this left, negative partial x, rho vx squared. That's the first one, okay? And see here, inside is some kind of rho vx squared. And the second one is rho vx vy. So minus rho v specs vy minus partial z rho vx z. Now the stress partial x y zx and z, pressure, gradient, and gravity, rho g. So that's the equation we got, okay? All right? So look at the first, look at the derivative on the left. And of course, you know why this is equal to this. This is simple calculus, right? So the differentiation of a product, and that's how you do it, right? So, and with the first term on the right, that's basically this, right? Rho v specs squared. And we can also do this, since it's a product, we'll consider rho vx together, and vx is a separate part. Okay? So differentiation of the product. So let me write all of them so you can see. The rho v specs, vy, so we have v specs, vy, and vy, plus rho vy, vx, and vy. And the last one on the right is this derivative, rho vx, vz, v specs, partial vz, vz plus rho vz, v specs, vz. The reason why I wrote all of them out, okay, without telling you, well, you can do the math, we won't do it. Because I want you to see the first terms on the right. On the right. Okay, so you look at these. Okay? Now why do we look at these? Because, see, if I move all these terms, all these three to the left, we have what? The summation of all these four terms, right? So basically, if I move those three to the left, we'll have the summation of these three terms. So basically, we add them together, right? You add them together, of course, you can see all these four, they all have v sub x, right? You can factor the v sub x out. You will have the summation of this, that, and that the root of partial rho, partial t. Okay? What is that? Right here. See? You move these three to the left, you basically have partial rho, partial t, plus that, and that. And that is what we just saw. Right? So factor the v sub x out. The summation of these four terms is what? 0, right? That's basically the equation of continuity. That's how you simplify this equation, okay? All right? So you move those three terms to the left because you add them together. See, these four added together will be 0. All we have left is that, and that, okay? So, and then you factor the rho out, and this is what we have. Sorry, this is one. So they equal partial p, partial x plus negative. And the stress term. Okay? All right, so this is the momentum conservation in the x direction, right? So the x component of the momentum conservation gave us this equation, all right? So this represents the momentum conservation in the 3D sort of control volume, okay? All right, so later we'll talk about what these terms mean, okay? But before we do that, of course, you know, we can do the same thing in the y and z direction, right? Okay? If we do this in the y direction, of course, this would be y, and y, and y, and this would be y. So this would be xy, yy, and yz, rho gy, right? So do this also in the z direction. So, and of course, we won't do that. So the same derivation can be done in the y and z directions. And then you will have what? You will have handout number 6, the problem, at least. Okay? So you see this is the first equation we just write in the y direction and in the z direction. So that's the rectangular for the system. Okay? All right? And this is what's called the equation of motion. Okay? All right? So, of course, once you derive this equation, you can also write it into the vector form. And this is what you see here. Of course, you're not required to know how to work with an equation like that. All you need to know is to work with equations like this. Okay? So that's the vector form of the equation. The advantage of writing it in the vector form is not only because it's concise and nice, okay? It's also because vector equations can be used in any coordinate system. So once you get this equation, you write it in the vector form, and you can put this in different coordinate systems and get new equations, okay? Now, of course, another way to do this, another way to get these equations in a cylindrical and spherical coordinate system is what? Is to do what we just did. Meaning that in the cylindrical coordinate system, you select a control volume in that coordinate system. Okay, so I gave you those two sort of MATLAB figures you can play with, right? So these are the control volumes. And then you look at what? Momentum in and out, generation, consumption, okay? The same as we did here, okay? And then you end up with these equations, okay, in these two coordinate systems. So two ways you can do this, but we won't do that, of course. So we just need to know how to use these equations, okay? All right? So this is the equation of motion. So together, these are called the equation of motion. So that means for a problem, instead of what? Using the shell balance method to go through the momentum conservation and mass conservation and everything, we can just what? Use these equations, okay? As you can see, in the derivation of this equation, did we say what kind of fluid it is? Nope. Okay, so that means this equation can be used for Newtonian or non-Newtonian fluids. Okay, all right. Of course, there you know for different kinds of fluids, you have a different relationship between tau and the velocity, right? Okay, so. Now, a special case for a fluid that has constant rho, that's rho density, and mu. Then we know Newton's law can be used, right? Constant viscosity, right? So that's Newton's law. Since in this case we know how, if you know this is a Newtonian fluid, that means what? You know how the stress and the velocity are related, right? So that's kind of number 2 or 3, right? Newton's law. So, and then you can plug that relationship, Newton's law, into this equation of motion. All right? So let me show you. It's true. Nope. Nope. There. Okay. Since for a fluid that has constant rho and mu, right? Okay. We know how the stress and velocity are related, right? All you need to do is to plug these into that equation, okay? And then stress will be gone. See, you plug that tau xx, tau yx, and tau zx here, stress will be gone. All we have left is an equation about velocity, okay? So then you'll get the Navier-Stokes we're going to get a new set of equations, right? And that set of equations is called the Navier-Stokes equation. So these are in handout number 7, okay? So equation of motion for a Newtonian fluid with constant rho and mu. They didn't say this is the Navier-Stokes, but it is called the Navier-Stokes equation. So as you can see here, the stress will be gone. They're replaced by the velocities, okay? So you plug the Newton's law in here. Others remain the same. See, the left-hand side, the pressure gradient, the gravity, only this is different, okay? That's the Laplacian of the velocity, right? Okay, so there. All right, so that's the vector form. So 3 components, okay? All right, cylindrical and spherical, okay? All right, so what do these terms mean? By the derivation of this equation, you kind of know what they mean already, okay? So let's start with the simplest. Well, that's gravity, okay? So that's gravitational force, or body force, okay? All right? This is what? The force due to pressure, okay? So this basically is what? Like force balance. Every one of them represents force per volume, right? Because we started with what? During the derivation, see, we started with force, okay? And then we divided by volume. So that's why in that equation, they all force per volume. That's the unit, okay? All right? So every term has force per volume unit. So everyone basically is a force per volume, okay? So gravitational force per volume, pressure force per volume, okay? As you know, pressure is force per area. So partial x is so force per volume. So gravitational force, pressure force. This is what? The force due to viscosity, so force by that, this is called the viscous force, okay? The force due to the viscosity of the fluid, okay? And what is this? Well, you've got the first term, rho, partial x, partial t, okay? This is like mass per volume times acceleration. So in physics, this is called the inertial force, right? Okay, all right? These are what? The convection, right? Remember, rho vx, that's convection, right? So this is still inertial force, but due to convection, okay? This is basically due to the change of the velocity over time. And this is due to location change, okay? So people pushing on each other, okay? So, all right? So let me write this down, okay? So remember, this is handout number 6. I hope you wrote this down already, okay? So rho, so this is the inertial force, rho dx, partial dx, partial x. This is the inertial force due to convection. And of course, that is due to what? The temporal change in the velocity. And partial p, partial x, that's called the pressure force, and mu, every one of them respects x squared. That's the viscous force. So these are what these terms mean in the Navier-Stokes equation. Okay, so the gravitational, which is x, so of course that's the gravitational force. It's also called the body force. Maybe I should be more precise. Gravity gravitational. Oops. So then you can compare these forces, okay, and look at relatively who is larger, who is smaller. Okay, for example, you can compare the inertial force due to the temporal change in velocity to convection and look at which one's bigger. You can compare this pressure force and inertial and any two. Okay, by doing that, you can get a bunch of dimensionless numbers, right? Because every ratio is dimensionless. Okay, so one of them that we did before is which one? The viscous force and the inertial force, right? So remember, if you look at the ratio between the inertial force and the viscous force, that's the inertial force, right? Rho, U, U, L. Representative or characteristic values of these variables. Rho, U, U, L, right? Or here, it's the same thing. That's because once you have L and U, you also get the characteristic time, which is L over U. You use it here, you get the same thing, okay? Viscous force, right here, mu, U, length squared, right? So you look at these two, the inertial force and the viscous force, we would have mu, U, L squared. So this is inertial force over viscous force, rho U L over mu, right? So, doesn't matter, you get there. This is what? Reynolds number, right? So one of the most important numbers in moment transfer. It's important because very often people would compare these two rather than any of those other combinations of two. Okay. Occasionally you still do it, but this is the most common comparison that people do. Yes.
Oh, what is the U mean again? Like the.
It's the characteristic velocity. Okay, so we talked about these actually. I forgot it was 1 or 2 lecture, or 2 or 3. Anyway, so there we used momentum transport and what? So convection and viscous, right? Or molecular interactions. Okay. All right. So Reynolds number. If you calculate this number and you find out the Reynolds number is much less than 1. Okay, meaning it could be 0.01 or could be even smaller. Okay? This means what? Which force is dominant? The viscous force is dominant. Okay? So order wins, or so viscous force dominant is dominant. That means the inertial force is much smaller. So the inertial force can be neglected. Okay? So that's the advantage of doing these comparisons, so that you can simplify these equations. Okay? So in this case, the flow is called the Stokes flow. Or the low Reynolds number flow. This kind of flow is one of my favorites. Why? Because the whole left-hand side of the Navier-Stokes equation is gone. Okay? Because the inertial force is much smaller than that, so the whole left-hand side is equal to 0. Okay? And of course, the problem is much simpler. And now, in what sort of circumstances this will tend to happen? Well, you can kind of see it from here. Okay? When this number is really, really small, that means what? Generally, this won't be very small. Okay? So these are common numbers. So it's here. Okay? It's when the length scale is very small, this number tends to be small. Right? When the length scale is small, unless you have a very large velocity, you will have a Reynolds number that's not much less than 1. Okay? So what kind of problems will give us small length scales? Well, I work with single cells and molecules. Well, there you go. Okay? So problems on the order of, length scales are on the order of microns, or even smaller. Okay? So one of the examples that we will talk about later is the cell sedimentation problem. So basically, if you put a cell in plasma, and because of gravity, it's going to go down, right? So small scale problem. So there, the Reynolds number is much less than 1. Of course, if you have the case of Reynolds number much less than 1, there could be also cases where the Reynolds number is much larger than 1. Okay? Now, in this case, which force can be neglected? Of course, it's the other one. In this case, the inertial force is much larger than the viscous force. So then the viscous force can be neglected. And this kind of flow is called the Euler flow. Since we have neglected the viscous force, so viscosity doesn't really matter anymore. In other words, you can consider the fluid as like no viscosity, okay? If it's no viscosity, it's called inviscid. And one example here is the airflow. Along airplane wings, okay? And of course, we won't look at that, okay? And if you ever wonder why St. Louis, one day is very cold, one day is very hot, it's all because of airflow, convection, okay? So for meteorologists, okay, some meteorologists, they may know, well, some meteorologists may know some momentum transfer, but all they use is some software that are developed by engineers. Okay. So, anyway, so there, this will be more important. Okay. All right, so now we've used about the lecture time to derive the equation of continuity and the equation of motion and the Navier-Stokes equations. Okay, so the whole reason is so that we won't have to use the shell balance method for every problem we want to solve. Okay, and now we can use these equations. I can tell you right now, we won't be using the equation of motion, the one with stress, a lot. Okay, because we're not going to use this to solve any non-Newtonian flow. It's too complicated. So all we will ever use will be the equation of continuity and the Navier-Stokes equations, meaning that we're going to look at some Newtonian fluid flows with these equations so that I can show you how to use these equations. Okay, so, all right. This next example, you will find it's very familiar because it's the same problem we looked at before. The steady state flow of a Newtonian fluid through a circular tube. Okay? The reason is that before we solved this problem using the shell balance method. Now I want to show you, if we want to use the equation of continuity and Navier-Stokes, how we're going to solve this problem. Well, it's cylindrical. That means we're going to solve these equations. Now, how many unknowns are in this equation? 4. Velocity, 3 components, plus what? Pressure. Others are known, right? Gravity, viscosity, and density. Okay? So 4 unknowns, you need one more equation. That one more equation is the equation of continuity. So you put these 4 equations together, this one plus those 3, 4 equations and 4 unknowns. Okay? It's a closed system. You should have a solution. Of course, we cannot solve these equations analytically in general. So for this problem, we can do simplifications, okay? Although I didn't write it here, but you know that problem we looked at it. The problem we looked at is in steady state, okay? Now, steady state, in math, it simply means this, right? No change over time. So no change over time. So look at this equation, this is what? 0. Okay? It's constant rho, so rho doesn't really have to stay inside. Rho can be canceled, right? If this is 0, rho is a constant because we're considering Newtonian fluid with constant rho and mu. So rho is constant. So you have RVR, V theta, V zeta, right? And then you look at these equations, partial t is equal to 0, so that means this, and this, they're all 0, okay? So that's the first simplification we can do, steady state. Now for this problem, we also mentioned this, fully developed, right? So remember what that means. So that means the velocity profile, we know there should be a VZ, and fully developed means further along into the tube, eventually the velocity profile will not change anymore in the z direction, right? So that's what this means. Of course, if we want to translate this into math, it simply means partial VZ, partial Z equal to 0. Okay? Now before we go to those equations, let me mention a few things more. We know also this problem has axis symmetry, meaning that if you look at the tube flow along the direction of z, you rotate the tube, You close your eyes, you rotate the tube, you won't notice any difference. Axis symmetry, right? So in math, it means this root of 0, right? Okay? So now let's look at this again, the equation of continuity. So remember, this is 0. We talked about partial theta is 0, right? Okay? So this one is 0, okay? Partial theta. This is basically, rho is gone, right? As we discussed earlier. So this is partial VZ, partial Z, right? So, fully developed, this is 0 too, right? All we have left is what? This equals 0. This equals 0, it's a derivative, equals 0, meaning what? This is a constant, right? RVR is a constant. RVR is a constant, that means what? VR is 0, right? Because R is not 0. R ranges from 0 to capital R, right? Radius. RVR is equal to a constant. We know that's 0 because on the wall, VR is 0. So that constant has to be 0. Otherwise, on the wall, R times a finite velocity will not give you 0, right? So, okay, all right? So we know this is equal to 0, right? So that equals 0, meaning VR is always 0. So that means now from the equation of continuity, we get VR equals 0. Now if you didn't write the details, so you know this is equal to 0. Of course, you know this is equal to a constant, and then you can determine that constant by using one of the boundary conditions, right? So that you know that constant is 0. So that constant is 0, that means RVR equal to 0 all the time. Of course, R is not 0, then VR is 0. Okay, that's the reason. Okay? All right? So that means the equation of continuity is what? Is gone. Okay? From there, all we got is VR equals 0, that's it. Okay? So, all right. What else do we have? We also have plane symmetry. Okay? Meaning, for this cross section of the circular tube, that's the plane. Okay, if you consider the plane that goes through the axis of symmetry, the problem is also symmetric about that plane, right? So in other words, you look at this problem along the axis of symmetry. You close your eyes, you rotate this. Not rotate, sorry. You look at this half and the other half, they should behave the same way, okay? Right? This half and that half, there's no reason for you to think these two halves should be different. So that means if you have a V theta here, you have to have a V theta going that way too. That means V theta has to be 0. So you see all these simplifications we've done. Okay? This is important. VR is 0. And this is also important. V theta is 0. Okay? So this simply means the first two equations in the Navier-Stokes. Okay? So you can see here, this is 0 we talked about, right? VR is 0. So VR, V theta is 0. So the whole left-hand side is gone. Okay? This is right. VR 0, VR 0, VR 0, V theta 0, gravity. Okay? So let's say in that case, the gravity is pointing in a circular tube flow problem we considered before. In which direction is the gravity? Z direction, right? Remember, the tube is like vertical, the gravity is pointing in a Z direction. Right? So that means rho GR is 0. So the whole first equation The only term that's left is here. Okay? So from the Navier-Stokes equation, now the first one, all we have is 0 equal to that, right? Now remember, we have capital P defined as P minus rho GZ, right? That's the capital P we've wrote before. So partial P this equal to 0 also means this is equal to 0. Why? Because see, rho GZ, this term doesn't matter if you do derivative in the r direction, right? So basically, you can prove this by going from this side to that side. Put capital P here, you'll find out it's equal to that, right? That's where rho GZ, the derivative is with respect to r is 0, okay? So now the second equation. Second, this is 0. Remember, v theta is 0. V theta, v theta, v theta, v theta. Again, the whole left-hand side is gone. This is there. V theta, v theta, v theta. Vr, 0. Again, g in the theta direction, 0. So the whole second equation, this is the only term left. 1 over r, of course, that can be cancelled. And we can just write 0 equals to partial P, partial theta. So of course, again, we can write this as partial capital P, partial theta. That's because rho GZ again has nothing to do with partial theta. So third one, partial T, 0, partial VZ, partial R, but there's a VR here. We know this is 0, V theta, 0, partial VZ, partial Z, fully developed. So the, again, whole left-hand side is 0, okay? Partial Z, partial Z, partial R, that's okay. Partial theta, 0, right? So again, you have a partial Z, partial VZ, partial Z here, fully developed, 0, right? You can see for the third equation, we have 3 terms left. This, and that, okay? So the third one, 0 equals to negative this plus mu plus rho and g. Since g is in the z direction only, so we'll just use g. GZ is g, right? So and we can group the pressure and the gravity together, write that as capital P. And write the partial as derivatives. Now that's because you look at here, P does not depend on R. P does not depend on theta. We also know partial T is 0. P does not depend on T either. So that means P is only a function of Z, right? Okay. So that's why we can do that. Okay. Now for V sub Z, of course, you know, partial V Z, partial Z is 0, fully developed. Partial theta is 0, and partial VZ, partial T is also 0. So it means VZ is only a function of R. So, and that's why we can change the partial to direct derivatives here. So I'll stop here. We'll finish this next time.